Hello, my name is Chen Boan, and I'm a junior student from Department of Chemistry. This is my final report for solid-state material design and electronics for Chemists class, and my topic is the introduction to density functional tie binding method. The following representation will be mainly based on the pedagogical paper written by Professor Pekka Koskinen from Finland and published on Computational Materials Science in 2009 with the title of Density Functional Tie Binding for Beginners. When I was viewing papers regarding molecular simulation, inverse design, and recent machine learning works for computational chemistry, I encountered the DFTB method. It seems to be a very important topic in theoretical calculation. Hence, I decided to dive deeper into this area and explore the mathematical and physical detail of this calculation method to see how it benefits computational chemistry. The DFTB method is a LCAO approximation of Kohn-Sham equation with semi-empirical parametrization. It combines the ab initio concept of DFT and the efficiency of tie binding model. As DFT being probably the most famous method in computational chemistry, for large systems or even periodic solid materials, the calculations will be too time-consuming. For example, during my research in synthetic chemistry, we utilized DFT method to get an insight on the electronic structures of our new synthesized compound every now and then. However, in a 100-atom system, the structural optimization process is slow. Hence, a simplified version of DFT can provide us a useful and efficient tool when it comes to large structures, general chain screening, and even ML chaining in chemical space. Let's start with DFT and take a good look into the tie-binding formalism and practical parametrization. An equation formulated by Walter Kahn and Shen Lujiu in 1965 simplifies a 3n variable equation into a 3-dimensional one. They successfully describe state energy as a functional of electron density, which depends only on 3D coordinates. Under Born-Oppenheimer approximation, the total energy of a given state can be separated into electron and nucleus parts. Consider a fixed set of nuclei. The nucleus energy is then the ionic repulsion, E sub ii. The electron energy can be expressed as the sum of kinetic energy T, external potential V, and two electron interaction energy U. And these terms can further be transformed into the sum of non-interacting kinetic energy T sub s, external potential V sub ext, Hartree potential E sub h, and exchange correlation energy E sub xc. The Hartree potential is just two electron-coulomb interaction, and the exchange correlation energy includes all the remaining many-body interactions. We will utilize atomic units in the following derivation. In other words, the elementary charge E, the electron rest mass m sub e, reduced Planck constant h bar, and the permittivity 4 pi epsilon 0 are set to 1. In this system, the unit of length is in Bohr radius, and the unit of energy is in Hartree. In view of chemists, the electron density is represented as the sum of occupied orbitals squared, with occupation number F sub a expressed as Fermi-Dirac distribution, and the numerator 2 is on account of spin for closed shell cases. Each orbital must satisfy a Schrödinger equation with a similar expression. Subtract the double counting of Hartree and exchange correlation terms, we can then formulate the Kohn-Sham equation as follows. The total energy is equal to the sum of occupied orbital energy minus the double counting Hartree term and exchange correlation terms plus the overall exchange correlation energy and nucleus repulsion. Now we have the Kohn-Sham equation that can be solved in a self-consistent manner. After the derivation of DFT method, it is time for us to approximate this expression. In 1985, this equation is simplified by Harris, who is originally considered a two-fragment system with weak interaction. The total density can be approximated by the superposition of the two isolated fragments, n sub 0, which can be of course generalized to superposition of any number of isolated systems. Substituting the true density n with n sub 0 plus delta n, and define epsilon 0 sub a as a corresponding eigenenergy of n sub 0. After rearranging, expanding, and cancelling these potential terms, a new expression with dependence of delta n is obtained. Assuming the density error delta n is sufficiently small, we can expand the exchange correlation energy at n sub 0 as a functional Taylor series. In Harris' work, he found that the first-order terms cancel each other out nicely, while in 1998, Professor Elstner and co-workers kept the second-order terms and construct a self-consistent charge extension of DFT-B approximation. Finally, the sum of occupied eigenenergies is called band structure energy, E sub Bs. The zeroth-order Harris correction terms, including the ion-ion interaction, are called repulsive energy, E sub Rep. The second-order term regarding charge fluctuation and exchange correlation is called Coulomb energy, E sub Coul, and the third and higher-order term are truncated for now. The mathematical derivation of DFT-B approximation is now complete. Now let's see how in practice we can get the energy values. First, let's talk about band structure energy. In a chemical sense, the wave function per C sub A are obtained in a LCO manner. In a basis of all the atomic orbital phi, the single electron wave function is expressed as a linear combination of phi with coefficient C. Consider matrix element H0 sub mu nu. The band structure energy can then be expressed as matrix multiplication. As normal free atomic orbitals are too diffuse to describe bound electrons in a molecule or even a solid, the basis phi comes from a pseudo-atom with additional isotropic confining potential, usually quadratic, with the parameter r sub 0 chosen to be twice of the covalent radii. The pseudo-atom basis is calculated with DFT, and a set of more localized radial wave functions are obtained, pairing with spherical harmonic same as those of normal free atoms. The spherical symmetry ensures the matrix element integration can be calculated with Slater-Koster transformation. Next, for Coulomb energy, the density error delta n can be expressed as charge fluctuation for each atom. The charge difference for atom I, delta Q sub I, can be the integration of delta n over atomic volume omega sub I. As charging an atom results the total energy lost with Mulliken electronegativity chi as slope and twice of the chemical hardness eta as second derivative, which are the definition of these values. After breaking the Coulomb energy into contribution of each atom pairs, the on-site terms are just charge fluctuation squared times chemical hardness. Since we have a set of local functionals, the exchange correlation for off-diagonal terms vanish. If we assume local delta n is Gaussian, which is justified with smoothness up to 90% accuracy, the Coulomb energy is then the error function divided by atom distance. For continuity toward on-site terms, the coefficient sigma sub I is 1 over square root of 4 pi times eta. Define the new function gamma of R sub ij with combination of the on-side and off-diagonal terms. The total Coulomb energy is expressed as half of the sum of quadratic charge fluctuation times gamma for each atom pair ij. Finally, for the repulsive energy, which contains exchange correlation interaction, is obtained by fitting the repulsive force for each atom pair with the repulsive energy of dimer containing a corresponding bond. Since the value of the potential energy is not absolute, but relative. Also, other approximations with greater impact have been made. This final correction should not be considered to cancel the energy error, but to give the same dynamics of the structure. With the tight binding spirit of parametrization, and for the sake of transferability, the repulsive energy is kept short-ranged, and the cutoff distance R sub cut is introduced with the value of 1.5 times the dimer bond length. So far, we successfully parametrized each of the 3 terms in SCC DFTB energy expression. We can also express the atom charge fluctuation delta Q sub I as matrix element through Mulliken population analysis. Define the atomic electrostatic potential epsilon sub I, operator H1 sub mu nu as the average of epsilon sub I and epsilon sub j, and total Hamiltonian matrix H sub mu nu as sum of H0 sub mu nu and H1 sub mu nu times S sub mu nu. After applying the variational principle, the secular equation for DFTB method arises, which can also be solved in a self-consistent manner. Parameter adjustment can be made to reach higher accuracy or to include more interaction terms like van der Waals forces. Periodic condition can also be applied for the calculation of repetitive solid materials. With the help of density matrix ρ, we not only simplify the expression calculation, but we can also define new chemical parameters regarding bonding. The density matrix is the outer product of the ket vector, and the observable is the trace of ρ times the corresponding operator matrix. In the electron number case, if we sum only the diagonal term in atom I, i.e. trace sub I, we can get the Mulliken population. Intuitively, while the on-side term of the matrix ρs describe the charge density, the off-diagonal terms describe the bonding interaction between 2 atoms. Hence, the Mayer bond order is defined by summing the off-diagonal terms over all orbitals contributed to these 2 atoms. A more quantitative measurement is bond energy, which can be formulated as the released energy minus promotion energy. Last but not least, to include repulsive and all interactions, the concept of absolute atom classifies the total energy release, ERAL, into each atom and each bond, and separate the bond interaction evenly to the 2 corresponding atoms, getting AB sub I as how much energy atom I contributes to total binding. The author provided several simple molecules as examples using this model, with long-ranged interactions not listed. These parameters are not limited to DFTB methods, but work well when discussing electronic properties. Note that in this table, the Mayer bond orders are really close to the valence bond value. To sum up, we go through the derivation, approximation, and parametrization for a density functional tight binding method, and finally see some real calculation using it. The SCC DFTB method includes the second-order correction of density error, which is account of the charge fluctuation of the system. One of the important tie-binding features is the use of pseudoatom as wave function basis set. With an additional confining potential, the atomic orbital wave functions are less diffuse and more bounded. Although being an approximation with inevitably less accuracy than an ab initio method like DFT, DFTB method has its advantage that it strikes a balance between high accuracy and short calculation time. The semi-empirical parameters generally accelerate the process, so DFTB can reach higher efficiency that is suitable for a large system and longer time scales. People can also include higher order terms in the functional Taylor series expansion and obtain an improved version like DFTB3 established in 2011. As machine learning being the most important approach to solve a lot of problems, not only DFTB provides a quick way to generate a large quantity of dataset in chemical space for training, but mutually, machine learning also gives us parameter optimization with its algorithm. When used together, scanning of chemical and physical property for general chain is possible, and inverse design for material and catalyst will be soon feasible. In 2022, DFTB Plus software package was released as an open source containing a lot of functions that benefit all chemists and physicists all around the world. It includes numerous corrections beyond today's introduction, such as spin orbital coupling, dispersion, time-dependent DFTB, and so forth. Recently in my research, DFT has been utilized to analyze the electronic structure of newly synthesized compound and to predict the reaction barrier using transition state theorem. While most of the calculations gave satisfactory results, some of them had a hard time reaching convergence. Therefore, I will try to use DFTB plus in theoretical calculation when DFT fails. Also, I am very excited to see what DFTB can achieve in the near future. This is the end of our voyage with DFTB and my presentation today. Thank you.